In this framework, we're going to calculate the forces in each of the members through the resolution of joint method. First of all, draw a free body diagram. To do that, we will sketch the structure again and replace the fixed support at point A with two forces, one vertical and one horizontal. And the roller support at point F, we replace that with one vertical force. Now you can see in our free body diagram, the fixed support at point A has been replaced by two forces, HA and VA, for the horizontal and vertical forces at joint A. And at point F, we've replaced the roller support by one force, VF. Next thing is to prove that the structure is statically determinate, and for that we must count out the number of members, the number of reaction forces, and the number of joints. To count out the number of members, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 members. Number of reaction forces, we have at point A 2 reaction forces, and at F 1 reaction force, giving us a total of 3 reaction forces. Then counting out the number of joints, we have 1, 2, 3, 4, 5, 6 joints. Then M plus R is 9 plus 3, which gives you 12. 2J is 2 times 6, and it also gives you 12. 12 equals 12, therefore M plus R equals 2J, hence the structure is statically determinate. The next stage is to calculate the reaction forces, and to do that we consider the three equations for equilibrium. All the forces in the x direction must add up to give you 0, all the forces in the y direction must add up to give you 0, and taking moments about any point must add up to give you 0 for equilibrium as well. Remember the sign convention: forces going upwards are positive, downwards are negative, to the right is positive, and forces to the left are negative. For moments, clockwise moments are positive, anti-clockwise moments are negative. Applying the first of our equilibrium equations, namely all the forces in the x direction must add up to give you 0. Here we only have one horizontal force, it is HA. It is pointing to the right, therefore is positive. For equilibrium, all these forces must add up to give you 0, hence HA is a value of 0. Now applying the next equilibrium equation, all the forces in the y direction must add up to give you 0. Here we have 3 forces, VA and VF, going upwards, and the 5 kilonewtons acting downwards. VA and VF are acting upwards and therefore are positive. The 5 kilonewtons is acting downwards and therefore is negative. Rearranging the equation, we get VA plus VF equals 5 kilonewtons. If we can work out the value of one of the reaction forces, we can easily then work out the value of the other. Now applying the last equilibrium equation, moments about a point. Any point must add up to give you 0. Remember, moments are a force by a distance, and you must state which point you're taking moments about. In this framework, we're going to take moments about the first support, which is labelled point A. A with a little bent arrow over it is shorthand for taking moments about point A. Then, looking back at our free body diagram, HA and VA are applied at point A, offset distance is 0, so those two forces don't produce a moment. What does produce a moment is the 5 kilonewtons at point C, and the other reaction, VF, applied at point F. For these two forces, I'm going to write down the force and the distance from point A to that force. So for the 5 kilonewtons, the size is 5 kilonewtons and it's 2 meters from point A over to point C. And for the reaction, VF is the size of the force. The distance across is 6 meters. Those are the two forces that produce a moment. For equilibrium, these must add up to give you 0. Now we'll consider clockwise or anti-clockwise to help us solve this equation. Remember, clockwise moments are positive, anti-clockwise moments are negative. Going back to our diagram here, consider each of these forces in turn as though it were on a piece of string, holding the end of the string at point A. How would the 5 kilonewtons want to rotate around point A? It would want to go around in a clockwise manner, therefore is a clockwise moment. Looking at the other force, VF, again, consider it as on a piece of string. You're holding the piece of string at point A. How does the force VF want to rotate around point A? It would want to rotate around in an anti-clockwise manner, therefore is negative. Updating this into our equation and then rearranging the formula. So we have 10 minus 6 VF equals 0. 10 is equal to 6 VF, taking it to the other side, then dividing through by 6, we get VF 10 divided by 6, and that gives you 1.67 kilonewtons. Then taking our equilibrium equation, we have VA plus VF equals 5 kilonewtons. Substituting in our value for 1.67 for VF, and then rearranging our formula, taking the 1.67 over the equal sign, makes it negative, we get VA to be a value of 3.33 kilonewtons. So our reactions are HA is a value of 0, VA is a value of 3.33 kilonewtons, and VF is a value of 1.67 kilonewtons. With these reaction forces, we can then apply this to our framework and then consider each of the joints in turn to work out the forces in each of the members. In our framework, one of the assumptions that we use is that all the members are in tension, and onto each member we're going to draw a set of arrows representing tension. For that, a set of arrows will be pointing inwards towards each other. I'm going to draw this on each of the members, and this will help us with the resolution of joints. First, we're going to look at joint A, and we're going to consider the equilibrium of forces at joint A. Taking the joint A and drawing a separate free body diagram for joint A, we have the arrows as shown in our free body diagram. We have VA, HA, force in member AC, and the force in member AB. The angle between these two members is 45 degrees. HA we know to be 0. VA we know to be a value of 3.33 kilonewtons. Now what we're going to do is we're going to apply equilibrium equations. Essentially, all the forces in the x direction must add up to give you 0, and all the forces in the y direction must add up to give you 0 for equilibrium. As equilibrium applies everywhere, it applies to the whole structure. We use that to work out the reaction forces. Now we're looking at each joint. Each joint must also be in equilibrium. Shorthand notation. Instead of writing down sigma Fy equals 0, the upwards arrow is shorthand notation for resolving the forces vertically. And what we have is we have VA is going upwards, is positive, plus then force AB. Part of that force is going across, part of it's going vertically. The part that is going vertically is FAB sine your 45 degrees. For equilibrium, those two must add up to give you 0. VA we know to be a value of 3.33. Then we can take our equation and rearrange it and work out the first member force. Taking the 3.33 to the right hand side makes it negative, then divide through by sine 45 gives us force AB to be minus 4.71 kilonewtons. The negative sign indicates that it is a compression force rather than a tension force. Doing the same, now resolving forces horizontally. What we have from our free body diagram are three forces going horizontally. We have HA, positive, plus FAC, plus the part of the force AB which is going horizontally, which is FAB, cos of your angle, 45 degrees. We know HA to be 0, FAC plus FAB cos 45 equals 0. FAC is equal to minus FAB cos 45. Substituting in our value for force AB, it's minus 4.71 cos 45. Careful about the double negative, making it positive. FAC will then work out to be a value of 3.33 kilonewtons. Now we're going to look at the next joint, joint B, to try to resolve the forces at this location. First of all, we will do a freed bodied diagram showing the forces as they are as circled. We have a force BD, force BC, and force AB. Angles are 90 degrees or 45 degrees. Careful, we're going to use the angle of 45 degrees relative to the horizontal. Then we're going to resolve the forces vertically, first of all. Remember the notation, upwards forces are positive, downward forces are negative. So we have minus force BC minus force AB times the sine of the angle, 45 degrees. For equilibrium, they must add up to give you 0. Minus force BC minus force AB is minus 4.71 times the sine of 45 degrees. Double negative makes it positive, so minus force BC plus 3.33 equals 0. Take force BC to the other side, it goes from negative to positive. Force BC is 3.33 kilonewtons. Next, doing the horizontal resolve, force BD minus force AB times the cos of the angle, 45 degrees. For equilibrium, they must add up to give you 0. Force BD minus 4.71 times the cos 45 degrees equals 0. Force BD plus 3.33 equals 0. Take the 3.33 to the other side, and it's a negative 3.33 kilonewtons. Negative sign indicates it's a compression force. The next joint we're going to do is joint C, and isolating the forces at joint C. Will get us the free body diagram, which is force going upwards, force going downwards, one to the right, one to the left, and a diagonal force using the angle relative to the horizontal, 45 degrees. Labeling these forces, we have 5 kilonewtons acting downwards, force CE to the right. The diagonal force is force CD. Vertical force is force BC, and the horizontal force to the left is force AC. Resolving the forces, first of all we're going to start with resolving forces vertically. So we have positive force BC, take off 5 kilonewtons acting purely downwards. Then we've got force CD, it's acting upwards, but only part of it is acting upwards, so we have to resolve the force, and we use for that the sine of the angle, So it's force CD times the sine of 45 degrees. Those are the forces that are acting vertically, upwards or downwards. For equilibrium, they must add up to give you 0. Force BC we know to be 3.33. Taking the difference between the numbers, 3.33 minus 5 gives you minus 1.67. Taking the minus 1.67 to the right hand side becomes positive. Then finally dividing through by sine 45 gives us force CD to be 2.36 kilonewtons. Now, using the same free body diagram, we're going to look at resolving the forces horizontally, and we have 1, 2, 3 forces acting horizontally. We have force CE acting to the right, positive, force AC acting to the left, negative, and we have part of the force CD acting to the right. This time it's going to be the size of the force CD, times the cos of your angle, 45 degrees. For equilibrium, these forces must add up to give you 0. Force CE minus force AC, which is 3.33, plus then force CD, 2.36, times the cos of 45 degrees. Force CE minus 3.33 plus 1.67 equals 0. Force CE minus 1.67 equals 0. Taking it to the other side, force CE is 1.67 kilonewtons. The next joint we're going to look at is going to be joint E, and we're going to resolve the forces that are in joint E. First thing we'll do is to draw a freed body diagram of the joint. And we have two arrows, one going left, one going right, and one going vertically upwards. These are labelled force CE, force EF, and force DE. Resolving the forces vertically and horizontally. Start with the vertical resolve. Force DE is the only force going upwards, positive. For equilibrium, it must add up to give you 0. Therefore, force DE equals 0. Then resolving the forces horizontally. we have minus force CE plus force EF, and for equilibrium these two must add up to give you 0. Force CE we know previously is a value of 1.67 kilonewtons, so substituting in that value and rearranging the equation, we get force EF, bringing the value to our side makes it positive, so it is also 1.67 kilonewtons. The next joint we're going to look at is joint F, and we're going to resolve the forces at joint F. First, we will draw a freed body diagram of the joint with the arrows as shown. VF previously worked out to be 1.67 kilonewtons. We have force EF going horizontally and force DF at an angle. The angle again is 45 degrees. Force DF is the last remaining member force to work out, and to work out force DF we just need to do a vertical resolve at this joint. Alternatively, you could do the horizontal resolve if you wanted to, but doing the vertical resolve we have force DF times the sine of the angle, 45 degrees. In this case it's positive because it's pointing upwards, plus force VF. Those are the two vertical forces acting upwards. For equilibrium they must add up to give you 0. Substituting in our value for VF that we have previously worked out, 1.67 kilonewtons, then rearranging the equation, making it negative on the other side of the equal sign, then force DF dividing through by sine 45 degrees gives us force DF to be minus 2.36 kilonewtons. Now at this stage we have all the member forces worked out. Previously at joint F we did the vertical resolve to work out the last member force. Now we're going to apply the horizontal resolve at joint F, and because we know all the member forces, if our values are correct they should all add up to give you 0. So what I mean by that is we're going to resolve the forces horizontally, minus force EF minus force DF times the cos of the angle. Those are the only two horizontal forces, both facing to the left, therefore negative. For equilibrium they should add up to give you 0. We know previously our force EF was a value of 1.67. Force DF we had worked out to be minus 2.36 kilonewtons times the cos of 45 should equal 0. And simplifying this we get minus 1.67 plus, when we do the calculation we get a plus 1.67, and that indeed does add up to give you 0. Therefore that gives us confidence in all our calculated values being correct, because our final check adds up to give us 0. If we had made a mistake somewhere in our resolving the joints and a member force, this last check wouldn't work out or give you anywhere close to 0.